Okay, moving on to 3 dimensions in our vectors. Very similar to 2 dimensions, just adding on an extra component onto it. So before, I had x and y axes, which corresponded to unit vectors I and j. Now I'm simply adding on a z component or a k unit vector. Okay. Now, as we move forward, just note at this point, we'll talk more about this later, that the orientation of these axes have to be in this way. I mean, it can be rotated certain directions, but the positive x, positive y, positive z all have to be in that orientation relative to one another. Again, you can rotate it one way, but again, they have to be in that relative orientation. And we'll talk much more about that when we talk about the right-hand rule as it pertains to moments. But for now, just remember that's how it has to be. Once I have those set up, really, I can break up my A vector that I have right here into the x component, y component, and z component, just like I did in 2 dimensions, and write that vector as axi plus ayj plus azk. This is exactly the same as 2 dimensions. It's just got this third component on the end of it, the z component, that I have to include as well. Okay, but nothing conceptually new here. Okay. Now, in order to find the magnitude of it, really nothing conceptually new here. It's still just Pythagorean theorem. But in 3 dimensions, I have to do a little bit of extra work here. Okay. So if I look down here, I've got 2 right triangles. I've got this gray right triangle that is laying on the xy plane. And then I have this vertical blue right triangle. And they share this side right here, this A prime side. And that A prime, if I look at the gray rectangle, is the hypotenuse. So it would just be ax squared plus ay squared square root to find the length of this side. Okay. Now, this side and this side, okay, sum up to the hypotenuse on this light blue triangle. So to find the hypotenuse, which is the magnitude of the vector of interest, that's just going to be a prime squared plus az squared, the length of this side and the length of this guy. Well, plugging in what I know about a prime squared, this magnitude A is simply ax squared plus ay squared plus az squared. And that's Pythagorean theorem in 3 dimensions. I oftentimes refer to it as square root of the sum of the squares because that's what holds true in 2 dimensions, 3 dimensions, and really mathematically 4 or 5 infinite number of dimensions. We'll never go more than 3 dimensions. I call it square root of the sum of the squares. That's how we find the magnitude of any vector. Okay. Now, these coordinate direction angles I really don't like. I actually prefer you use this notation when writing a 3-dimensional vector. I get more from this than I do from the coordinate direction angles. However, you should know what coordinate direction angles are, knowing that moving forward I won't use them very much, if at all. Okay, and what coordinate direction angles are if I have my A vector, it's the direct angle between the x-axis, the positive x-axis, and that angle. So alpha goes from the x-axis to A, beta goes from the positive y-axis to A, and gamma goes from the positive z-axis to A. Now I've got these right triangles here. Okay, that's a adjacent angle to the y, adjacent angle to the x, adjacent angle to the z. Okay, so I use cosine in order to find these angles. So cosine of alpha is ax over a, cosine of beta is ay over a, cosine of gamma is az over a, where a again is the magnitude of the total vector, and these are the components of each. Again, I'm not a big fan of these because those angles are really hard to conceptualize and visualize, whereas the ax, ay, az I think is actually easier for you to kind of figure out what direction the vector is going in. But that is, if it asks for coordinate direction angles, that's how you find them. And that's just how you can define angles in 3 dimensions. In 2 dimensions, those angles make a lot of sense. In 3 dimensions, it makes it a little challenging. Okay. Now, addition of these vectors works exactly the same as 2 dimensions. Again, I'm just adding this final term on here. So when adding these vectors, I'm going to sum up all the x components, sum up all the y components, and now I'll sum up all the z components, okay, to get that resultant vector. Exact same procedure, just a 3rd dimension. Okay, so in this example, we're going to determine the magnitude and coordinate direction angles of the resultant force of these two forces. So we do this exactly the same way that we did in 2 dimensions. We just have this z component. And that is, we start by summing the force, or we sum the forces, yes, but we start by writing the forces in Cartesian form. So we'll start with F1, okay? And F1 is given like this. So I've got this dark blue triangle, this light blue triangle, okay? I've got a right angle right here on the dark blue triangle, and I've got a right angle right here on the light blue triangle, okay? So I can break this up. Here's my x component, here's my y component, and here's my z component. So it's going to be plus x minus y plus z. So I have plus, minus, plus. That's where that comes from. Okay. Now I need to know the length of the side of this triangle, and this triangle. The z component is actually the easiest component. The hypotenuse of this triangle is 80. Okay. The z component is opposite of 30. So it's going to be 80 sine 30, which is I have right here in the z component. Okay. Now, again, remember that prime axis. This is the hypotenuse of the dark triangle and the adjacent leg of the light triangle. So the length of this side is actually 80 cosine 30. Okay. And you see that 80 cosine 30 shows up in both the x and the y components right here. That's the length of this side. That's actually the hypotenuse of this triangle. So when trying to figure out the y and the x-axis is adjacent to the 40 degrees. So I take this hypotenuse, 80 cosine 30, times the cosine of 40 to find the length of the x component. Likewise, the y component is opposite of 40, so it's going to be sine 40. Okay, the hypotenuse is 80 cosine 30, right, times the sine of 40 because it's opposite of it. So this big long equation here is actually the F1 written in Cartesian form. And you can plug that in your calculator and actually get numbers. Now F2 is very simple. It's just acting downward in the negative z direction, so I just get minus 130k. So once I've written both vectors in Cartesian form, I simply add up the x, add up the y's, add up the j's. So adding up the x's, the 53.1 is just what I've got here because there's no x here. Okay. Adding up the j components, the 44.5 is simply this because I'm adding it to 0j into F2. Okay. And this would be 40 minus 130 gives me the minus 90 in the k direction. So my resultant force is actually given right here. It's 53.1I minus 44.5J minus 90K. And in fact, I prefer this sort of way of writing it. But the problem does ask for the magnitude and the coordinate direction angle. So moving forward, the magnitude is simply the square root of the sum of the squares. So 53.1 squared plus 44.5 squared plus 90 squared equals 114. That's the magnitude of the resultant of these two things added together. Okay. Again, I prefer this sort of writing. This gives me a better idea of what direction things are going in. But if I do want to find those coordinate direction angle, I just use those equations we talked about in the lecture. Alpha, beta, gamma is just going to be the inverse cosine of ax over a, ay over a, and az over a. So I get the 53.1, negative 44.5, negative 90. Plugging those into your calculator, I get these angles. Now the problem is these angles are really hard to visualize. Once I go beyond 90 degrees, it becomes very challenging for me to actually visualize what this direction actually is, which again leads me back to what I said, where I prefer this sort of representation of the vector. But the problem asks for the magnitude given here and the coordinate direction given here. In this problem, we want to determine the magnitude of the resultant force of these two forces added together, F1 and F2. Now these are in 3 dimensions, so the way we're going to start this is write each force in Cartesian form, and then we'll sum up the x, y, and z components to find our resultant force. So we'll start with F1. Okay. And F1 is only in the x direction and the negative z direction. Okay, so it's 300 cosine, because it's adjacent to the x-axis, cosine of 30 in the I, 300 cosine 30i. Nothing in the j direction. It's lying in the xz plane, so there's no component in the y direction. And then I've got a negative k of 300 sine 30 given there. Okay, and then here are the numbers for that calculated out. Okay, moving on to force 2. Now this is actually done in 2 steps. Okay, so you notice I've got a light blue triangle and a dark blue triangle. Okay, the light blue triangle lies in the xy plane, and the dark blue triangle is basically a vertical triangle. This line right here on the edge of the dark blue, that is in the z direction. That is f sub z. Okay, so if the hypotenuse of this right triangle is right here, that is 500. That means the fz component is opposite that, so it's going to be 500 sine 45, and that's in the negative z direction. So you see right here we have the 500 sine of 45. Again, that's this line right here. Now this side of the triangle, of the light blue triangle, that's my x component of the force, and this is the y component of the force. Okay, this is the hypotenuse of that light blue triangle. It's also the adjacent side of the dark blue triangle. So the length of this line right here, which is the hypotenuse of the light triangle and the adjacent side of the dark triangle, this is 500 cosine 45. Okay, and I get that from this 500 newtons. Okay, it's adjacent to the 45, so that's 500 cosine of 45. Now I use that hypotenuse to find the x-axis, which is opposite of the 30 degrees. Okay, so I'm going to take that value, the 500 cosine 45, times the sine of 30, because it's the opposite side. And that's what I have right here. 500 cosine 45, that's this line right here for the dark blue triangle, times the sine of 30, because the x component is opposite of that 30. That makes this side 500 cosine 45 times the cosine of 30, because this one's adjacent to the 30. So again, what I have here is 500 cosine 45. Again, that's this leg of the triangle. Okay, that I get from the F2's 500. Okay, then cosine 30, because the y component is adjacent to 30 here. Okay, and that's in the j direction. Okay, so I have those, and I can calculate those given right here. There are the numbers for F2. So now I've got the F1 and F2. Now, in order to find the resultant, I simply sum up my i's, sum up my j's, and sum up my k's, as shown here. So here, here's F1 calculated up here, and here's F2. So I, take I plus I, 0 plus this j, and then this k plus this k, and I get this as my resultant force. Okay. Then to find the magnitude of that resultant force, I just use the square root of the sum of the squares. So square root of x squared, y component squared, z component squared. There should be a little plus sign in here. It's a little typo here. Okay, so plugging that in here, I determine that the magnitude of the resultant force is 733 newtons. So again, I just break my forces up into Cartesian form, sum up my x's, sum up my y's, sum up my z's, and then square root of the sum of the squares to find the magnitude.